In this exciting edition, we will be looking at the box on a ramp problem. This is really an archetype of a problem. This technique that I'm going to show you can be used to deal with any kind of dynamics problem that is a problem involving forces and accelerations. So the general idea is we are going to want to find the acceleration of a box, and that box, that was not a very straight line. So we're going to place our box on a ramp. So I'm actually just going to draw a straight line. So here's our ramp. And I'm going to do this numerically at first to give the idea, but we, of course, as always, need to be prepared to deal with things that are not numeric. So then I'm going to stick a box on the ramp. And there it is. So some basic assumptions for this problem. We're going to assume that there's no friction. No friction. Okay, writing too high. So on this surface, we are going to have no friction. We will add friction in, and really at the end of the day, adding friction in isn't that big a deal. So we're going to have no friction. We're going to say that the mass of the box is 10 kilograms, just for the sake of having numbers. And we're going to say that this angle is 30 degrees because that will make it easier to deal with this in the long term. Okay, what are we trying to accomplish? Well, to start with, we are going to try to find the acceleration of the box. If it is not completely obvious, this box is going to accelerate. We might not be able to see it now, but once we draw the force diagram, it should become completely obvious that, yes, in fact, this thing must be accelerating. So we have a situation, we're looking for the acceleration. We don't know anything about time, we don't know anything about velocity, we don't know anything about position. All we know about is forces. So draw a force diagram. I'm going to start with what I would like is a dotted line. That's alright though. Okay, so I'm going to start my force diagram by putting in my object. Here's my object. This is the box. I'm now going to follow the procedure outlined in the reading that we did earlier on, and I'm going to put in my x-axis parallel to the surface. So this dotted line is the surface, and it is my x-axis, and again, here is my object. A big force diagram is a good force diagram. I'm then going to put in my y-axis perpendicular to my x-axis. So there's my y-axis. I would like to get this number on there, so I'm also going to put in my horizontal and vertical. It's a little bit hard to keep these lines straight on the computer, but there's my horizontal and vertical, and I can see that this angle from horizontal to my ramp, is 30 degrees. That's going to be important here in a minute. I'm just trying to get the information organized onto my force diagram. So, I'm going to get my forces. Looking at the box, declaring that to be my system, there are two things interacting with the box. There's the earth, and there's the ramp, which is our surface. So as I draw in those forces, switching colors here, we have the force of gravity straight down, Fg, the force of gravity of the earth on the box. We also have the force of the surface, which is the normal force. The word normal means perpendicular to the surface. The normal force is always perpendicular to the surface. Here's the surface. If I can figure out how to, there we go. Here's the surface. We want our normal force to be perpendicular to that. So there's my normal force up at this angle. Gravity's done, ramp is done, I'm fresh out of forces. So this is it. At this point, it should be completely obvious that in fact the box is going to accelerate down the hill. F net equals ma. there is no way that this force and this force can add together to give this 0. This one, well, right now it looks like this one is at an angle, but we're actually going to treat this one like it's off angle. So these being vectors, F net ma, this isn't one equation. We always treat motion directionally. We do vectors one component at a time. So we know that F net in the x direction is ma in the x direction, and F net in the y direction is equal to ma in the y direction. So we're now ready to take this thing on. Okay, I just need to go get my forces and figure out where do they go over here. I know the mass, it's right there. I'm looking for the acceleration, which is right here. I just need to get my forces in order. Well, let's take care of the y first. We actually already know ay. Because I have defined my y-axis to be that direction, we know that there will be no motion in that direction. So this ay is actually just 0. And while this isn't terribly interesting now, in future problems this is actually an important step. So in the y direction, the forces have to add to 0. So let's look at our forces and see where they go. Well, Fn is in the y direction, and it's up. So I can put that over here on my Fn side, F net y. F net y is the normal force minus, well, not the entirety of gravity. Gravity is not pointing along the x or the y-axis, it's straight down. So we need to break that thing into components. The vertical component is right there. It is just this leg of the right triangle right there, breaking this vector into components which are along the y and x axis. So this one is Fg in the y direction, and this one is Fg in the x direction, right there. So in the y direction we have Fn up, Fgy down. That has to be equal to 0. So, well, again, in this problem it isn't terribly interesting. We know that the normal force has to be equal to only the vertical component of gravity. And again, as a reminder of the normal force is exactly as big as it needs to be. In this case, it doesn't have to be as large as the mass of the box, or as the weight of the box. It only has to be as large as the vertical component of the weight. Well, let's look in our x direction. We have only one force. It's right there. Fgx is in our x direction. That is going to account for our acceleration. We just need to go ahead and get a number for this since we are looking for an actual number. So we need to find, well, what is Fgx? Well, I know so far that it is the component of Fg. So if I knew Fg, and I knew this angle right there, I should be able to find Fgx. And it turns out that I know both of those things. I know that, clearing up a little bit of space here since I don't actually need all that, I know that Fg, assuming that this box is on Earth, is 9.8 times the mass, and actually for ease of use I'm just going to use 10. I honestly don't have a calculator on me, so I'm going to go ahead and use 10. Fg is 10 times the mass. Well, I know the mass is 10 kilograms, so the weight of the object is about 100 newtons. So the hypotenuse of my triangle is 100 newtons. I'm not looking for the hypotenuse, I'm looking for the opposite side. So to get that, oh, cannot see my mouse. Where is my mouse? There it is. So to get this Fgx, I actually need to look at this right triangle. I know that sine of the angle is equal to Fgx over 100. I just need to know this angle. Well, here we go. I should have drawn this bigger. Here's the x-axis. There's the y-axis. Those are 90 degrees from each other. If this is 30, this bit is 60. Here's horizontal, here's vertical. If this bit is 60, this bit must be 30. Here's horizontal, here's vertical. That bit is 60, so this angle right here should actually be 30 degrees. So I know that FGX, solving for FGX, is 100 times the sine of 30 degrees. That's got to be MAX. And I know that 100 sine 30, I know that sine 30 is 1/2, so this is 50. 50 newtons has to be 10 kilograms times my acceleration in the x direction. 50 newtons divided by 10 kilograms gives me an acceleration of 5 meters per second squared in the x direction. We already knew AY is 0, so here's the answer to our problem. Find the acceleration of the box, 5 meters per second squared. That is how you approach any sort of problem like this. You're dealing with forces and you want to find acceleration.